we're exploring the fascinating world of fractals. You know, those incredibly detailed patterns, the ones that seem to repeat themselves endlessly no matter how close you look.
Yeah, they're really stunning visually.
Totally mind-boggling. And our mission today is really to unlock the core mathematical secrets behind these intricate, often beautiful shapes.
Think of it as a shortcut, maybe, to understanding the hidden logic.
Exactly, a sort of express ticket to understanding these seemingly bizarre forms.
And what's really captivating, I think, is that while they look amazing, they're rooted in some, well, pretty fundamental but powerful areas of math.
Like, what are we talking about?
We're talking geometry, obviously, the study of shapes, set theory, too, which is about collections of things, and something called complex dynamics.
Complex dynamics, okay.
Yeah, it explores how things evolve over time, through mathematical rules. It's pretty deep.
Okay, let's start to unpack this then. One of the real driving forces you mentioned behind creating fractals is this idea of iteration.
That's it.
It sounds a bit technical maybe, but is it just repeating things?
At its heart, yeah. It's simply doing the same thing over and over again. Repetition.
Okay.
And when we talk about iterated function systems, or IFS for short, this repetition gets more structured.
IFS.
Got it, yeah. Imagine you've got a set of instructions, specifically these things called affine transformations.
Affine transformations, okay.
Think of them as like mathematical ways to resize, rotate, shift things around, maybe even skew them a bit.
So changing the shape.
Changing its position, size, orientation. But the crucial part, the really key idea, is that these transformations are usually contractive.
Contractive, meaning they shrink.
Exactly. They shrink distances between points. Imagine folding a piece of paper over and over. The distance between any two spots gets smaller each time.
Right, right. It collapses inwards.
That's the idea. Contractive.
So, okay, how does this repeated shrinking and moving and stuff actually build one of these infinitely detailed fractals? It seems like a jump.
Well, the process itself has a certain elegance, I think. You begin with a simple starting shape. Could be anything, really. A square, a triangle, even just a point sometimes.
Okay, simple start.
Then you take that shape and you apply each of your affine transformations to it. So you get several smaller transformed versions of your original shape.
Multiple copies, but smaller and maybe rotated or moved.
Precisely. Then, here's the key step. You replace your original shape with the combined result, like the union of all these smaller copies.
Ah, okay. So the old one disappears, replaced by the new little ones.
You got it. And then you just repeat.
Repeat the whole thing on the new collection of shapes.
On the new collection, the output becomes the new input, infinitely.
So it's kind of like a, I don't know, a sophisticated photocopier that also shrinks and rearranges the copies. And you just keep feeding the output back into the machine forever.
That's a fantastic way to think about it, yeah. And what's so remarkable is that even though you started simple, as you repeat this shrinking and rearranging, this incredibly detailed, complex, fractal structure just emerges.
It just appears from the process.
It does. A perfect example to picture this is the Sierpinski triangle. You probably know that one.
Oh, yeah, the triangle with the hole.
That's the one. You start with a solid triangle. Then you apply rules that basically create 3 half-sized copies of it.
Okay.
And you arrange them so they leave a triangular hole in the middle pointing downwards.
Right, you remove the middle fourth.
Exactly.
Yeah.
And then you just repeat that process on each of the 3 smaller triangles you just made. And on the smaller ones inside those, and so on.
And what you end up with is this beautiful, intricate pattern of triangles within triangles, seemingly going on forever. Forever.
That leads perfectly into another key characteristic, right? Self-similarity. It's like these shapes have miniature versions of themselves hidden inside at different scales. Precisely. And this self-similarity, it actually comes in a few different flavors, you could say.
Oh, it's not all the same.
Not quite. There's strict self-similarity. That's when the fractal looks absolutely perfectly identical at any magnification.
Any zoom level, it's the same pattern.
Exactly the same. Think of the Koch snowflake. Every little zigzag on the edge is just a smaller version of the entire snowflake shape.
Okay, like a perfect miniature.
Or the Sierpinski gasket or triangle we just talked about.
Yeah.
You see that same triangle with holes pattern no matter how much you zoom in. That's strict self-similarity.
Okay. Then you said there are other types.
Yeah, then we have quasi-self-similarity.
Quasi, meaning sort of.
Sort of, yeah. Approximately the same at different scales, but not perfectly identical. The Mandelbrot set is the classic example here.
Ah, the famous one.
That's it. As you zoom into the Mandelbrot set, you'll see recurring patterns, little shapes that look like the whole set, themes repeating. but they won't be exact, perfect replicas. Similar, but distorted or slightly different.
I see, like echoes rather than copies.
Good way to put it, echoes. And finally, there's statistical self-similarity.
Statistical. Okay, that sounds a bit more abstract.
It is, but it's also maybe the most common type you see in the natural world. It means that certain statistical properties stay consistent across different scales.
Statistical properties. Like what?
Like its roughness or jaggedness. We quantify this with something called the fractal dimension. We'll get to that. So a coastline, for example.
Right, the classic example.
It won't look exactly the same from space as it does when you're walking on the beach, obviously.
Yeah.
But its overall degree of jaggedness, statistically, will be similar across those scales.
So the amount of wiggliness stays the same, relatively speaking.
Pretty much, yeah. Think of mountains, the branching of trees, river networks. These often show statistical self-similarity.
Fascinating. So nature uses this too.
Absolutely. And all these forms of self-similarity, whether strict, quasi, or statistical, they all ultimately arise from that fundamental iterative process we talked about, applying the same rules over and over, just at smaller and smaller scales.
Okay, so we've got iteration repeating rules and self-similarity shapes echoing themselves. But then we had this really, this mind-bending concept you mentioned, fractal dimension.
Ah, yes. This is where it gets really interesting.
The idea that a shape can have a dimension that isn't a whole number. Like, how can something be, say, 1.5 dimensional? That just sounds wrong.
It does challenge our everyday intuition, doesn't it?
Yeah.
We're used to Euclidean dimensions. A line is one-dimensional, right? You can only move forward or back.
Yep, 1D.
A flat plane, like a piece of paper, is two-dimensional. Length and width, two directions.
2D. Got it.
A solid cube is three-dimensional. Length, width, height, 3D. These are nice whole numbers.
Right, simple.
Fractal dimension, though, can be a fraction, a non-integer. Think of it maybe like this. A fractal with a dimension like 1.5 is more complex than a simple 1D line. It tries to fill space like a 2D plane,
Okay.
but it's so infinitely crumpled or porous or jagged that it never quite manages to fill up a full 2 dimensions. It occupies this sort of in-between dimensional space.
So it's measuring complexity, or how much space it fills up as you zoom in.
Exactly. It quantifies how densely the fractal fills space or how complex its structure is, especially as you look closer and closer.
So back to the Sierpinski triangle. You said its dimension is around 1.585. That means it's definitely more than just a 1D line.
Oh, much more complex than a line.
But it doesn't completely fill a 2D area like a solid triangle would. It's got all those holes.
Precisely. It's in this fuzzy in-between state, dimensionally speaking.
How do mathematicians actually calculate this? Is there a formula?
There are a few ways. One formal definition is called the Hausdorff dimension. It's quite mathematically dense, based on covering the set with small balls and measuring how that cover scales.
Okay, maybe let's skip the dense math for now.
Probably wise. A much more intuitive approach, or at least easier to visualize, is the box counting dimension.
Box counting.
Yeah. Imagine you overlay your fractal with a grid of squares, like graph paper. Boxes of a certain size, let's say size epsilon.
Okay, I put a grid over it.
Then you just count how many of those boxes contain any part of the fractal. Let's call that number epsilon.
So count the boxes that touch the fractal.
Right. Then you make the boxes smaller, a smaller epsilon. And you count again. You'll need more boxes now, right?
Sure, yeah. More smaller boxes to cover the same shape.
The fractal dimension essentially tells you how quickly that number of boxes, epsilon, increases as the size of the boxes, epsilon, decreases. It's related to the limit of log epsilon divided by log 1 epsilon as epsilon gets tiny.
Okay, so it's about that relationship, how the count scales with the size.
Exactly. If you need way more boxes than you would for a line, but fewer than for a solid shape as you shrink the grid, that's the clue. The dimension is fractional.
That makes intuitive sense.
And even better, for those strictly self-similar fractals we talked about earlier, there's often a really neat, simpler formula. It's called the similarity dimension.
Okay.
If your fractal is made up of n identical copies of itself.
Like the 3 triangles in Sierpinski.
Exactly, n3 for Sierpinski. And each copy has been scaled down by a factor of r.
Which was 12 for Sierpinski.
Yeah, right again. Then the fractal dimension d is simply the logarithm of n divided by the logarithm of 1 over r, or log log magnification factor.
So for Sierpinski, d divided by log base 10 of 2, or natural log of 3 divided by natural log of 2.
Yeah, and it comes out to about 1.585.
Wow. So the formula confirms that intuitive idea. It sits right there between 1 and 2 dimensions.
Perfectly capturing its intricate nature. More than a line, less than a plane.
Okay, that's That's actually clearer now. Dimension isn't just 1, 2, 3. It's about complexity and scaling.
That's a great way to summarize it.
Right. Now, let's switch gears a bit. You mentioned these other famous fractals earlier, the escape time ones.
Yeah.
Like the Mandelbrot set and Julia sets.
Ah, yes. The superstars of the fractal world, maybe?
They look incredible, but they sound a bit different. They operate in the realm of complex numbers, right?
They do.
Maybe a quick refresher. What are complex numbers all about? Some of us might be a little rusty on that.
Sure, no problem. Think of regular numbers, integers, fractions, reals as living on a single line. The number line.
Okay.
Complex numbers basically expand that line into a whole two-dimensional plane, the complex plane.
So like coordinates.
Kinda. Each complex number has two parts. A real part, which is just a regular number on the number line, and an imaginary part. The imaginary part involves this special number I.
I, the square root of Mach 1, I remember that.
That's a 1. So a complex number typically looks like a plus pi, where a is the real part and b is the real coefficient of the imaginary unit I. You can plot this number at the point a, b on the complex plane.
Okay, so every point on this plane is a complex number.
Exactly. And these escape time fractals are generated by repeatedly applying a surprisingly simple formula within this complex plane. The classic one is Zn plus 1 equals Zn plus 1 equals Zn squared plus c.
Okay. What are Z and Kenki?
They are both complex numbers themselves. Z is the variable that changes with each iteration, and c is usually a constant for a given calculation.
And how do we get these incredibly detailed, stunning fractal images just by repeating that simple equation? It seems too simple.
The magic, or the mathematics, lies in how we classify the points in this complex plane based on what happens during that iteration.
Classify them how?
Well, for each starting point we're interested in, we begin the iteration. We plug the result back into the equation over and over and over. We watch what happens to the magnitude of the complex number z, its distance from the origin 0, 0 on the complex plane.
Okay, you track its distance.
If that distance grows larger and larger, heading off towards infinity, we say the point escapes, and that initial point is considered outside the fractal set.
It runs away.
Right. However, if the magnitude stays bounded, if it stays within a certain distance from the origin, no matter how many times we repeat the process, then that starting point is considered inside the set.
It stays trapped or contained.
Exactly. It remains bounded.
Okay, so for the Mandelbrot set specifically, what's the role of c in that equation? Zn plus 1 equals Zn plus c, and what's the starting z?
Right. The Mandelbrot set is a very specific definition. It's the collection of all possible complex numbers c.
So we're testing different c values now.
Yes. It's the set of all c values for which the iteration Zn plus 1 equals Zn plus c, starting specifically with 0 at 0.
Always start z at 0 for Mandelbrot.
Always.
Yeah.
For which that iteration remains bounded, doesn't escape to infinity.
So you pick a point c on the complex plane, you start z at 0, you calculate z1 equals 0 plus c, then z2 is z1 plus 1 plus c, then z3 is z3 to 0 plus c, and so on.
Keep going.
And if the distance of those e values from the origin never goes infinite, then that c you picked is in the Mandelbrot set.
You've got it perfectly. For every single point c you can imagine on the complex plane, you run this test. If the sequence stays bounded, c belongs to the set, usually shown as black in the pictures.
And what's truly incredible and what everyone recognizes is the boundary of this set. It's just infinitely complex.
Infinitely. No matter how much you zoom in on the edge, you find more detail, more complexity, often including tiny copies of the whole set itself, albeit distorted.
And the colors. The vibrant colors you always see.
The colors are usually assigned to the points outside the set. The color typically represents the escape time, how many iterations it takes for the magnitude of z to exceed a certain threshold, indicating it's escaping.
So faster escape means one color. Slower escape means another color.
Exactly. Points that escape quickly might be colored blue, slightly slower ones yellow, even slower red, and so on. The points inside the set, which never escape, are traditionally colored black.
That makes sense. So the color shows the speed of escape for points outside the black shape.
Precisely.
Okay. Then what about the Julia sets? You mentioned them too. How do they fit in? Are they related?
Very much related, but generated slightly differently. For Julia sets, we do the opposite in a way. We pick a fixed value for c first.
Okay, so c is constant for a given Julia set.
Right. Then for that one chosen c, we test every possible starting point 0 in the complex plane. We iterate the same formula, Zn plus 1 equals Zn plus c.
So now c is fixed, and we're varying the starting point z.
Exactly. And again, we track whether the sequence of z values starting from that 0 escapes to infinity or stays bounded. The Julia set, for that specific C is the set of all those starting zero values that remain bounded.
Ah, I see. So the Mandelbrot set is about which C values keep 0 equals 0 bounded, while a Julia set is about which zero values stay bounded for a fixed C.
Perfect summary.
Right.
And what's absolutely fascinating is how the shape of the Julia set changes dramatically depending on which C value you choose. Some are connected shapes, some are scattered dusts of points.
So each different C gives you potentially a completely different looking Julia fractal.
Completely different, yeah. And there's this really deep, profound connection between the Mandelbrot set and all these possible Julia sets.
Which is?
If the C value you choose to generate a Julia set happens to be inside the Mandelbrot set, then its corresponding Julia set will be connected. It will all be in one single piece, though possibly very complicated.
Connected, okay.
However, if the C value you choose lies outside the Mandelbrot set, then the corresponding Julia set breaks apart. It becomes a totally disconnected dust of points, something mathematicians call a Cantor set structure.
Wow. So the Mandelbrot set acts like a map or an index for the connectedness of all possible Julia sets.
That's a beautiful way to put it. It's exactly that, a map of Julia set morphology.
And you also mentioned something about Julia sets being boundaries.
Yes. Often the Julia set forms the boundary of what's called a basin of attraction. In these iterated systems, sometimes points get pulled towards a specific long-term behavior, like settling down to a fixed point or a cycle. The basin of attraction is the set of all the starting points that get pulled towards that specific behavior.
Okay.
The Julia set is often the incredibly complicated fractal boundary between different basins of attraction. Points right on the Julia set itself often have chaotic, unpredictable behavior.
So it separates regions that behave differently under iteration.
Exactly. It's the edge, the frontier.
This whole idea of iterating functions, especially in the complex plane, it really sounds like it unlocks a whole new area of mathematical exploration beyond just making pretty pictures.
Oh, absolutely. It's the heart of a field called complex dynamics.
Complex dynamics.
Yeah, which is the broader study of how functions behave when you apply them repeatedly, particularly in the complex plane. It goes way beyond just z plus c.
And what are some of the key concepts in complex dynamics?
Well, we look for things like fixed points, those special values z, where d, s, z. The function doesn't change them.
They stay put.
Right. We also look for periodic orbits or cycles. That's a set of distinct points that just cycle through each other when you apply the function over and over, like z1 goes to z2, z2 goes to z3, and z3 goes back to z1.
A repeating loop.
Exactly. And then we have these crucial concepts of attractors and repellers.
Attractors and repellers, okay.
Attractors are points, or cycles, or even more complicated sets, that nearby points get pulled towards as you iterate the function. Like mathematical magnets.
Pulling things in.
And repellers are the opposite. Nearby points tend to move away from them under iteration. They push things out.
Okay. And how do these relate to fractals?
Interestingly, Julia sets are often closely related to the collection of repelling periodic points of the function. They form sort of the skeleton of the chaotic dynamics.
The repelling points structure the Julia set?
In many cases, yes. And as we said before, the basins of attraction, the sets of starting points that get drawn towards a particular attractor, often have these Julia sets as their boundaries, the boundary between order and chaos, in a sense.
Fascinating. So complex dynamics provides the framework for understanding the behavior behind these fractal structures.
Precisely. It gives us the tools to analyze why they look the way they do and how the iteration behaves.
We've covered iterated function systems like the Sierpinski triangle and these amazing escape time fractals, Mandelbrot and Julia. But I know there are other ways these kinds of shapes can arise in math too, right? It's not just those two methods.
Definitely not. There are several other interesting ways fractals pop up. One method uses something called L-systems.
L-systems.
Or Lindenmayer systems. They offer a completely different approach, more symbolic. Think of them as sets of simple rules for rewriting strings of symbols, like letters in an alphabet.
Rewriting strings, how does that make a shape?
Well, you start with an initial string called the axiom, like just the letter A. Then you have rules, like A gets replaced by ABA, and B gets replaced by BBB.
Okay, substitution rules.
Right, you apply these rules over and over in parallel to the whole string. So A becomes ABA, then that becomes ABA, BBB, ABA, and so on. The strings get longer and more complex.
I see. But shapes?
Then you interpret these generated strings geometrically. Like A might mean draw a line forward, B might mean turn left, another symbol might mean turn right. As the string gets more complex, the geometric interpretation creates these intricate, often very organic and plant-like fractal patterns.
Ah, so it's like a symbolic recipe or a genetic code for geometric growth.
Exactly. It's a blueprint encoded in symbols that unfolds with each iteration. Very powerful for modeling things like plant growth.
Cool. What else?
Then you have random fractals, which, well, as the name suggests, incorporate an element of chance or randomness into their construction.
So not deterministic like the others.
Not purely. Think back to that coastline example. It has fractal characteristics of fractal dimension, but it's not perfectly self-similar in a predictable, rule-based way like Sierpinski. There's randomness involved in its formation.
Okay. Nature's randomness.
Right. Or think about Brownian motion, the random jiggling path of a tiny particle suspended in fluid. That path turns out to be a fractal.
Really? A random walk is fractal?
Statistically, yes. And computer algorithms can use randomness deliberately to create very realistic-looking fractal landscapes for movies or games, for example. The fractal dimension here becomes more of a statistical measure of that randomness and complexity.
Got it. Randomness adds another layer. And one more type.
Newton fractals are another interesting class.
Newton, like Isaac Newton. Related to his method for finding roots.
Exactly that. Newton's method is a powerful iterative technique for finding the roots, the solutions, of polynomial equations, like finding where x31 equals 0.
Okay. How does that make a fractal?
If you apply Newton's method in the complex plane to find the roots of a polynomial, well, a polynomial can have multiple complex roots. You want to know which starting points in the complex plane lead to which root when you iterate Newton's method.
So mapping out the basins of attraction for the roots.
Precisely. And it turns out that the boundaries between these basins of attraction, the regions that converge to different roots, often form beautiful and surprisingly intricate fractal patterns.
So the dividing lines between where you end up are fractals themselves.
Yes. These Newton fractals separate the complex plane into the basins of attraction for each root. Another case where boundaries become fractal.
It's amazing how many different mathematical ideas and tools seem to converge when you start talking about fractals.
It truly is a crossroads of mathematical concepts.
Yeah.
You really see set theory providing the foundation, right? Defining fractals as specific sets of points with these unique properties.
Okay, sets are fundamental.
Then topology comes in, giving us the language to talk about connectedness, and crucially, the concept of dimension itself, allowing for these non-integer values.
Topology handles the shapes and dimensions.
Measure theory offers the rigorous framework for actually calculating and understanding fractal dimension, especially through ideas like the Hausdorff measure we briefly mentioned.
Measure theory for the dimensions. Got it.
And then real and complex analysis are absolutely essential. You can't do iteration, convergence, limits, or deal with the complex numbers needed for Mandelbrot and Julia sets without analysis.
Analysis provides the engine for iteration and limits.
Definitely. And finally, pulling back a bit, you see connections to nonlinear dynamics and chaos theory. They help us understand how these incredibly complex patterns can emerge from seemingly simple, deterministic, but nonlinear rules.
Like Z plus C.
Exactly. And how fractals often appear as attractors, or basin boundaries, in chaotic systems. It highlights that extreme sensitivity to initial conditions that's characteristic of chaos. Tiny changes can lead to vastly different outcomes, often related to which side of a fractal boundary you start on.
Wow. It really touches almost every major area of modern math.
It really does blend them in powerful ways.
Okay, so just to kind of wrap our heads around this, we've taken a pretty deep dive into the core ideas behind fractals. We started with the power of iteration, just repeating simple rules.
The engine behind it all.
Then we looked at self-similarity, how these shapes echo themselves, whether perfectly, approximately, or statistically.
A key visual characteristic.
We wrestled with that really mind-bending idea of non-integer fractal dimensions, using box counting and similarity dimension to see how they quantify complexity and space-filling properties.
Moving beyond 1, 2, 3 dimensions.
And we explored the stunning complexity of escape-time fractals, like Mandelbrot and Julia sets, born from simple iterations in the complex plane, revealing connections to complex dynamics, attractors, and basins.
Yeah, Z plus C creating infinite worlds.
And it's just so important, isn't it, to recognize that the math behind all this is this potent blend of diverse fields, set theory, topology, analysis, dynamics.
It really pulls them together, giving us this language to describe structures with infinite detail, which is something classical geometry couldn't really handle.
Right. They really challenge our traditional, maybe more rigid Euclidean ideas about geometry, pushing us to think differently about dimension, shape, and boundary.
They force a new perspective.
It's truly remarkable that these infinitely detailed structures can emerge from such concise, often elegant mathematical rules, the complexity hiding in simplicity.
That's one of the most profound aspects, I think.
And maybe as a final thought for you, the listener, to ponder, consider how this core idea of self-similarity might appear in unexpected places. Maybe outside mathematics entirely. In nature, sure, but maybe in social structures, in art, in music.
Interesting question.
Or perhaps, how does this concept of infinite detail, structure within structure at every scale, how might that change the way you perceive the world around you, from the incredibly small to the unimaginably vast?
It definitely makes you look closer.
Something to think about. Thanks for exploring this deep dive into the mathematics of fractals with us today.